Okay, great. So thanks, Alicia. So very happy to have Tom Purdy with us today, the JQI seminar. So Tom did his PhD at UC Berkeley. He was working on things like cavity QED with ultra-cold atoms and atom chip systems. He then went to JILA. He studied basically measurement and control of micromechanical systems, demonstrating squeezing, optical squeezing, and back action effects. Then he was at NIST, actually. He was in this room many times, I think for 4 years at NIST, as a staff member, basically working on quantum measurement and nanomechanical systems. Then I think about 2.5 years ago, he went to Pitt, where he's leading a research group and always has a lot of interesting things to say. And I'm very much looking forward to his talk. So let's welcome Tom.
Okay, great. Thank you for the introduction. I hope everything is working properly. People can hear me at different locations. Okay, people in the live audience are nodding, so I'll assume everyone on Zoom is also nodding. But anyway, I'm Tom Purdy. I have a lab that specializes in quantum optomechanics and quantum transducers at the University of Pittsburgh. To distract you from a fairly boring title, I try to put some cute pictures of my little witch on this title slide. Also, the reason why this talk may not be as polished as it might otherwise have been. Let's see. Okay, great. Slide advance is working. So let me introduce the Purdy Lab team. I'm going to talk about 3 different projects today that we're working on. The first project was, I'm sorry, still trying to get used to this pointer. What was led by my former postdoc now, Ravi Singh, who was at JQI for several years. As of, I think, next week, he's moving to NIST Boulder to work on some other projects. The second project is spearheaded by Sean Howe, a graduate student in my lab. The third part of the project is led by these 3 guys, Angad, Mahir, and Yang. We also have some undergraduates and at least one former Purdy Lab group member, Jingchen Zhang, who's now at Maryland, actually in the audience here. Let's see. So my lab, we try and do, basically we make sensors, mechanical sensors that operate at very high sensitivity. We understand the quantum limits of those sensors, and ultimately we want to make measurements of mechanical things that are very hard to measure: gravity, dark matter, spontaneous decoherence in quantum mechanical systems. Those are sort of our big picture goals: making quantum networks with quantum transducers. But we haven't made much progress. I've been at Pitt about two years. So I think today's talks will be a little bit more nuts and bolts, talk about projects that we're working on related to the first steps in those projects. So part 1 will be about what I call acoustic blackbody radiation. So most folks are familiar with the electromagnetic blackbody radiation. Things glow when they get hot. Turns out that things make noise when they get hot too. I'll talk more about that. The second part, we'll talk about the quantum optical lever. So the optical lever is just a really old optical measurement technique used to measure the deflection of light off of some tilting surface. We'll start to understand the quantum limits of that kind of measurement technique. And at the end, if we have any time left, I'll tell you about some quantum transducer projects we're getting started in my lab, where we are trying to interconvert microwave and optical photons to have them superconducting qubits talk via optical networks. But likely we won't have much time for that at the end. Okay, so part 1, acoustic blackbody radiation. So you guys are probably all familiar. You see something glowing red. You say, "Oh, I see that's glowing red. It must be hot. It must be emitting blackbody radiation." You don't typically put your ear up right next to this object, get real close, not so close that you burn yourself, and listen, and you don't hear clackling and hissing and popping, and say that's a static, and say that's real loud. It must be hot. But I claim that everything that's emitting electromagnetic blackbody radiation is also emitting acoustic waves, sound noise. And so this project is really about, can we explore the analogs between electromagnetic blackbody radiation and the acoustic equivalent? And to do that, we need something that I call an acoustic blackbody. And what's an acoustic blackbody? It's nothing but a lossy piece of material, acoustically lossy, something that can efficiently absorb and emit acoustic waves. And for us, this is a little blob of epoxy composite, so it's basically goo and dirt, and that's a pretty good absorber of sound waves. So this object is a thermally occupied blob, and what it's doing is it's jiggling about. You can think all of its normal modes or all its individual molecules, kind of randomly jiggling about. It's sitting on some type of substrate, and all the jiggling about causes force on the substrate, which causes acoustic waves to be emitted into the substrate. And that's what we call acoustic blackbody radiation. So this is all in vacuum. We're not thinking about sound through air today. We're thinking about sound through solids. In order to make experimental progress on this, we need some detector of this acoustic blackbody radiation. Turns out we don't think about it in our daily lives because it's typically really, really tiny. So we need actually a pretty good detector of acoustic energy or acoustic waves in order to detect these fairly small, random thermal acoustic noise inside our substrate. And to do that, we use a fairly simple optomechanical system. What I have here is a picture of a thin piece of a silicon nitride stretched over a hole in our substrate, makes a little drum, and that has a bunch of normal modes of motion. And those normal modes can be excited by acoustic waves in the substrate. Read it out with a fairly straightforward optical detection technique. We use an optical lever, and this put together could be the equivalent of an acoustic blackbody radiation thermometer, just like we have these non-contact infrared thermometers. What we're trying to build is something that can measure the acoustic radiation from some hot blackbody with some sort of a sensitive detector. So
Tom,
that's the setup.
This is Bill Phillips. I'm just wondering, is LIGO doing the same thing? That is, we hear about the noise in the mirror coatings and stuff, and it sounds like it might be the same thing. Is it?
So the distinction I'm making is that my acoustic blackbody is remote from the object that's being measured. We have a physical separation. Basically, if you have any nanomechanical resonator, it's going to be thermally occupied. And it's going to be thermally occupied. It's going to be driven by some bath. The question is that bath sort of physically internal to the object, or is it external? Is it, some physical object I can pinpoint over in some distant location, and there's an exchange of energy and acoustic waves back and forth. So that's what I'm saying, is that we want to study this phenomenon. Not just that we're not just generally studying thermally occupied mechanical resonators, but the tricky part is that it's often really hard to distinguish what the source of what your bath is. And in this case, I think it is geometrically like this. It's distinct that we can fiddle with the acoustic blackbody independent of the silicon nitride membrane, independent of our detector.
Gotcha. Thanks.
Yeah. So let's think a little bit about our detector before we get into the details of this. And let me even go back a step and say that I'd say this type of idea is somewhat underappreciated at least in nanomechanics, also in many other contexts, and that this is I would say a perfectly valid method of heat sinking. So we talk about radiative cooling of an object. When we talk about radiative cooling, we instinctively believe electromagnetic radiation cooling, but this system, it turns out, will be the dominant source of dissipation is for our nanomechanical resonator here, our silicon nitride membrane drum. The dominant source of dissipation by far, by 3 orders of magnitude, is this acoustic radiation. So it's in a very different limit than a lot of other systems. So where we can quantitatively study what's going on. But so what's going on is we have this silicon nitride membrane. And it oscillates with some normal mode. We picked out a particular normal mode of here that has about 10 antinodes along one direction and one antinode along the other direction. We label that the 110 mode, just to distinguish it from all other normal modes of a square drum. And we do some finite element simulations that we put this embed the silicon nitride membrane inside a silicon substrate. And what this shows here is what's emitted is a preferentially horizontal beam of acoustic waves traveling through the substrate. So we often call this our optomechanical antenna. It's a directional emitter of acoustic waves into a substrate. So it's also what we call a reciprocal antenna, meaning that if we were to provide acoustic waves in the same focusing pattern now, going back towards our device, it would efficiently it would efficiently couple to those waves and be excited. So it's an emitter and an absorber of acoustic waves, our little nanomechanical detector. Okay, so just generally we can think about these guys as antennas. They have some directionality. It's very roughly a diffraction limited wave traveling through a square aperture, spreading out in space. Importantly, we have a mode that, oh, sorry, not to give too much away. Here we go. Sorry, still getting this laser pointer working. There's also a mode where we rotate this entire diagram by 90 degrees. And there's a mode that would emit efficiently up and down and not out horizontally. We call that the 10-1 mode. There's a lot of different modes we can look at, and there'll be a couple of different radiation patterns. Okay, so I said we want a device whose dissipation is dominated by this acoustic radiation channel. And we chose the silicon nitride membrane because it has a very large internal quality factor. It has about a internal Q of 10 million if you ignore this acoustic radiation. Let's see here, we got a picture of that. A mechanical ring down. This is a few hundred kilohertz mechanical device, and we can excite it and we can watch it ring down for minutes, and that's because it has a very high intrinsic quality factor. What this picture is over here is taking a silicon nitride membrane on a silicon frame and embedding it in this other lattice of aluminum squares. We call this a phononic crystal lattice. The idea is that this acts like an acoustic mirror to keep all of our acoustic energy inside of our silicon and our silicon nitride, and none of it escapes further than that. And this is a periodic array of scatterers for acoustic waves. It acts like a phononic band structure, and actually we have a large band gap at the wavelengths that we care about for this experiment. The important figure of merit is that the internal quality factor must be much larger than our radiative quality factor. Here, we're measuring the internal quality factor of our silicon nitride plus our silicon. So it's saying our silicon is also a very transparent medium. In order to have radiation coherently, ballistically transported from one place to another, we have to have a transparent medium. In this case, single crystal silicon, a nice transparent medium. And we'll compare this Q of 10 million to what we get when we have an acoustic black body absorbing all this energy. It'll be much bigger. Okay, so first problem experimentally run into, I did this nice simulation for effectively putting an infinite structure that our acoustic radiation is allowed to be emitted into. If you say the domain of my object is just some finite square of silicon, well, the waves reach the boundaries, they bounce off, and they form some complicated interference pattern on the substrate, which is interesting, but not particularly experimentally fun to deal with. So Ravi Singh spent a lot of time designing acoustic black bodies to put on the surface to have high emissivity and high absorptivity, that they very effectively absorb this acoustic radiation in a single pass. And this is what he came up with. We have some oblong blobs of this mechanically glossy material. We put them around the substrate in the pattern shown. And here's just a simulation of the acoustic waves that are emitted by our nanomechanical resonator, and they're mostly absorbed by two of our black bodies and mostly ignored by what we call the vertically oriented black bodies. Again, this is supposed to be a reciprocal device, so the black bodies are jiggling about randomly, and they are also emitting energy into the mode that's accepted by our nanomechanical resonator.
Are there any differences between, so now like on the right, very much like the image on the left?
Yeah, that's the whole.
So close to the to your silicon nitride. Are there any like key differences in the modes? Oscillation between the infinite extent and this.
The silicon nitride membrane looks effectively identical in both cases.
I'm sorry, not silicon nitride, I guess the silicon.
The idea is we try to make these as close as possible, and we'll get to we'll get to a slide in the future which tells us about the directionality, how much of the energy is actually absorbed in these horizontal black bodies versus the vertical ones, and it's pretty good. About 99% is absorbed by the horizontal black bodies, and 1% is absorbed by the vertical black bodies. So it is still a pretty good directional antenna. Okay, so here's what it looks like in reality: a millimeter square of silicon nitride stretched over a hole in a silicon frame with some blobs of epoxy around it. Okay, and here's our first measurement. What we do is we optically detect the motion of our mechanical resonator, and we take the spectrum of that, and this is zoomed in around here. This is these red curves. Let's see, here we go. Over here is zoomed in frequency. The spectrum, we see two Lorentzian peaks, which correspond to the thermally occupied mechanical motion of our nanomechanical resonator for two modes, the 110 mode, which we think emits horizontally, and the 10-1 mode, which we think emits vertically. If we take the area under this curve, we can use the equipetition theorem to tell us how much energy it has or what the temperature is. So we can do a Brownian-motion thermometry. These have approximately the same temperature at the moment, but what we do is, let's see, a few things here. A few things to note before we talk about the experiment. We can look at the width of these, spectral width of these features now, and they're no longer corresponding to a Q of 10 million, they're corresponding to a Q of about 10,000. So this tells us that this is good experimental evidence that our energy is being dissipated by these acoustic black bodies. Take them off the substrate, we have a Q of 10 million, put them on, we have a Q of 10,000, very roughly speaking.
Sorry, how are you obtaining this box? Like, what physics quantity are you measuring?
This is the let's see. So we use we use an optical lever to detect the tilt of the local tilt of the surface of the membrane, and we detect that on a split or quadrant photodetector, and we take that signal, digitize it, and Fourier transform it, and take the power spectrum. We average that many times over to get the average power spectrum. Good. Let's see. Yeah, so we do that, and then that's good evidence. The Q goes down, but we can do even better. What we can do is do an experiment, which I think really proves that what we're doing is acoustic blackbody radiation thermometry, meaning that we can, if we look at the left half of this diagram, we can heat up one of these acoustic blackbodies above room temperature. We shine a laser on it, it absorbs some power, it gets hot. Turns out the rest of the substrate, the rest of the device, the other acoustic blackbodies stay at room temperature, and we can look at the mode temperature of different silicon nitride modes. And importantly, at time zero, we turn on our heating laser, and what happens is that the mode that's coupled to the radiation emitted by our hot acoustic blackbody gets hotter. So I'm having trouble with this laser pointer. The mode that's supposed to be coupled to the acoustic blackbodies that stay cold stays at the same temperature. And we can do the converse experiment where we heat up a different mechanical mode that's supposed to be coupled to a different, we heat up a different black body, which is supposed to be coupled to a different mechanical mode. And indeed, the other one gets hot and the first one stays cold. So this is really our smoking gun evidence that what we're doing is changing the temperature of a device, not by heating the device itself up, by heating the bath that it's coupled to up. So we're doing acoustic blackbody radiation thermometry. And so this is good evidence. This is very good evidence that indeed we make this remote acoustic heat sinking channel, which is, I think, experimentally useful, especially at low temperatures where other channels of heat sinking, the diffusive flow of heat becomes very low at cryogenic temperatures where thermal conductivities become low. This channel stays constant roughly. It's not affected by the mechanical properties too much.
By mode temperature, is it the temperature of the the blob that you're eating?
So the mode temperature we're measuring is the area under this Lorentzian. That's what we say is the mode temperature. It's we get the expectation about the mean square displacement, and then from that we extract a temperature using equipetition theorem. And so it's not the temperature of the silicon nitride that we're measuring; it's the temperature of the mode, and the temperature of any mode. So we go back to a fluctuation dissipation theorem, which says that wherever energy is dissipated, the thermal fluctuations from that bath or that object are the ones that are actually driving thermal motion of our mechanical system when it's in thermal equilibrium with that bath. And it turns out, if you heat the bath up, the temperature of the mode gets hotter because that's where its dissipation occurs. And the evidence that we haven't actually heated up just our entire system says that some of our modes stay at constant temperature.
It's not.
Tom?
Yes.
I'm a little bit confused. You said that those noise spectra looked Lorentzian.
Yeah.
But doesn't the mean square of the Lorentzian diverge, or is it only Lorentzian close in?
So experimentally, we are fitting the curve you see there with signal noise of a couple to find the area under the curve. But generally, for a harmonic oscillator, this equipetition theorem holds, and the total area under the curve should be 1/2 m omega squared, expectation value of x squared equal to half kBt. Yeah, so I've worried about this in the past, and what we can say is that there may be some other noise hiding in the wings that's hard to experimentally measure. And what we say is the noise spectral density is consistent with a certain equilibrium temperature over the range of frequencies where we have good signal to noise. And the noise spectral density over the range of frequencies where we have good signal noise goes up, and we ascribe a higher effective temperature to that mode more precisely. So I can't claim the integral overall frequency generally is not something that's experimentally accessible. That is true. But I think just looking at the spectral density near the peak can also give you a good indication of the temperature.
Sure, but what I'm wondering is, why would I expect it to be Lorentzian as opposed to, say, Gaussian?
The noise, well, this is just so the general model is that we have a white force noise. That's just generally true of most thermal noise sources, or it's broadband, at least compared to our line widths, when our line widths are pretty narrow here. So if we have a broadband white force noise, then the equilibrium spectrum should just look like that force noise multiplied by a harmonic oscillator response function.
Okay, right. So
it's not exactly Lorentzian, it's a harmonic oscillator response function.
Okay. Okay, thanks.
Yeah, sorry. So in practice, we fit to Lorentzian since we're talking about high Qs, and near the peak, the Lorentzian is indistinguishable from the true harmonic oscillator response function.
Are you only measuring and showing trends on one hand, or is it somehow that you only generate?
So this is just, the spectrum is just cropped in around those two frequencies. So they're supposed to be nominally degenerate. If it's a perfect square, those two frequencies are right on top of each other. This is a very, very slightly different than a perfect square. So those two modes are really near in frequency, but not exactly on top of each other. And this is actually a plot over here, a spectrogram. So this is the spectrum versus time from when we turn our heating laser pulse on. We actually can measure the spectrum, then we turn it off and we watch it cool down. And you can see other black curves here represent other mechanical modes. Another question.
The bits while the laser's on, is that deformation of the membrane due to heating?
Yeah, exactly. So the question was here, why do these modes bend in my spectrogram? And that's indeed because when I heat up my acoustic black body, that thermally expands a little bit and tugs on the substrate, which changes the stress in the membrane in a slightly non-uniform way and changes the frequency a little bit. And to get this answer right, we do actually have to take into account the in our equipetition theorem the current mechanical frequency. So we're actually in a limit where the temperature is changing slow compared to the mechanical decay rate. So the mechanical decay rate here is still faster than the thermal equilibration time of our device. So we assume that for short periods of time where we're making our measurement, even for those sort of millisecond timescales where we're taking a measurement, averaging over, that our device is in equilibrium with whatever is causing its heating. So yeah, that's important that these timescales are separated to easily analyze an experiment like this. Okay, so this was a smoking gun signature that we're doing acoustic blackbody radiation thermometry. Some people call it a small effect. I would say it's instead it's a small change in a big effect, because pretty much all of this motion it should be the ratio of the intrinsic Q to the radiative Q, and that's about a factor of 1,000. Pretty much all of this noise is due to acoustic blackbody radiation. We're just only able to change the temperature of the blackbody radiator by a small amount. Let's see. So why do we care about this? I don't have a ton of time to talk about this, but in previous experiments at NIST, in collaboration with Cardiac Stream Boston and Jake Taylor, we built some other Brownian-motion thermometers that had some nice properties. We measured the Brownian-motion of a nanomechanical resonator optically, and we turned it into what we call something that's starting to approach a primary temperature standard, meaning one that's self-calibrated. And I don't have any time to go into this, but we're actually able to measure the optical back action on our mechanical resonator. And a Heisenberg uncertainty principle tells us the size of that back action is related to the size of the 0-point motion mechanical resonator. And so basically what we're doing is measuring the RMS occupation in with a scale which is a vibrational quanta or 0-point motion. And we get that out just by taking correlations of our data, and taking just pure ratios of correlations of data and fundamental constants. We get our temperature in Kelvin, at least at the proof of principle a few percent level. The idea is that we want to use this nanomechanical detector to detect the temperature of a macroscopic object. In this case, we're going to combine acoustic blackbody radiation thermometry with this primary, with this self-calibrating idea, and come out with a perhaps practical temperature sensor that takes a nanomechanical object, single nanomechanical degree of freedom, and couples it to a big macroscopic acoustic blackbody or something the size of a centimeter die, a really macroscopic object, and it measures the temperature of that. And that's a much more practical, useful thermometer. Thermodynamics happens in the limit of big things. So you wouldn't like to make a thermometer that only measures a tiny nanomechanical degree of freedom. You like to use one that can come in contact with a big object and measure the object's temperature. Let's see. So that's what I want to say about this acoustic blackbody radiation idea. I want to switch topics now. Talk about another topic, which is really closer to sort of quantum measurement. That was, very much classical noise, although still think it's quite a practically useful object. But the optical lever, I want to talk about that for a few minutes, and the quantum limits here. So optical lever, I'm going to assume most of you guys or most of you folks are familiar with this idea that if I bounce light off of some tilting object, I can measure it on what we call a quadrant photodetector. That is a detector that's broken up into 4 segments, and I can count the amount of photons on the left half versus the amount of photons on the right half. This is useful in atomic force microscopy, in precision metrology, your big G torsional balance, in industrial metrology, autocollimators all use this idea. But it's a really old technology. I would claim it's one of the oldest precision measurement techniques, using angular deviations of light in the sharp edges to figure out stuff about time, about space. Really Stone Age technology. People have been using that for quite a while. We want to understand the quantum limits. And no one's really thought too hard about the quantum limits, experimentally at least, for this type of detection, is because no one's had an optical lever system that where it's become relevant. And over the last couple of years, there's been a lot of engineering in nanomechanical systems to make them incredibly high quality factor, make them incredibly low mass, allow them to bounce light off them with high reflectivity, in such a way that it now becomes relevant that the back action from the measurement, that is the optical force noise, can become hopefully comparable to or larger than, say, the thermal noise driving a mechanical resonator. They don't have to worry about the back action. We're not experimentally there yet, but we think we could be, so we think it's worth starting to understand this. So our prototypical system will be a laser and a Gaussian beam, and it's bouncing off one of the sine wave mode of a high tension string. So it's a flat string, so there's enough surface area we can focus a laser and bounce off. We focus it locally such that it looks like it's roughly tilting off it's bouncing off a flat tilting surface, and we measure it with a quadrant photodetector. And so what are the quantum limits of this?
Is there a reason why it's a quadrant photodetector and not, like, I guess, could you not cut it up into more little?
Very good question. We'll get to that in just a few slides. I'll tell you why you don't need to do that. It only gains you a tiny bit, turns out. So some quick facts about the optical lever. This first bullet point is actually getting at that in a vague, veiled way. It's actually within a factor of 2. Using quadrant photodetection is actually within about a factor of 2 of an ideal quantum measurement. And just if you don't realize this, optical lever detection is used because it's simple, robust, and it's actually pretty high signal to noise. So compared to focusing your light on the antinode of the string and analyzing that as part of a Mach-Zehnder interferometer, using the optical lever, if you set your beam up correctly, has a sensitivity within a factor of few, a shot noise limited sensitivity within a factor of a few of other single pass interferometers. So it's intrinsically not a bad thing to try. And the nice part is that it's insensitive to all sorts of classical optical noise. So it's fully differential. We don't worry about intensity noise. There's no frequency discriminating element. So we don't worry about frequency noise. It's just all we care about is the spatial mode. It turns out that the data I'm going to show you later is not even taken with a laser, it's taken with an LED, a temporally incoherent source. But no experimental system has yet reached interesting quantum back action limits in this sort of single pass optical lever detector. Okay, so here's the formal answer to the question as to how good is a quadrant photodetector. So we can actually write down. I'm no expert at all this higher sort of theory of quantum measurement. I'm an experimentalist. I like to measure photons and count shot noise and look at signals and noises. But you can formally calculate something called the quantum Fisher information, which tells us how much information you could extract about the angular displacement of your beam by making a measurement of where photons land on some surface, on some detector surface. And there's something called the quantum Kramer bound, which tells you per photon how much angular what's the uncertainty in the angular deviation from your measurement. If you go ahead and calculate how much information you actually get by using a 2-pixel photodetector, so just the left and right half of a quadrant photodetector, it's actually about 0.64 of the quantum Fisher information. So we call that a 64% quantum efficiency detector. But all we're doing is saying, is a photon on the right or on the left? We're not saying how far to the right or how far to the left we can be. So we're already within a factor of 2 of the best we can do with just 2 pixels, which begs the question, if we go to a mini pixel array, just a CCD camera, well, that takes more cost. They're slower. For me, they're a little trickier to use the frequencies we care about. But can we improve this any further? Turns out we can improve a quadrant photodetector further with a very simple trick. And the idea is that basically, if we wanted to weight where our photons lie on our detector and figure out how much we should weight those, it turns out the photons that are further away from the center, we should weight more. Those have a larger deviation. And it turns out the best way to do things is a linear weighting. And what we actually have when you look at a quadrant photodetector is just a step function. If it's on the left, we say -1. If it's on the right, we say +1. We'd actually like to use a linear weighting. We can approximate a linear weighting in a photodetector basically just by sawing our photodetector in half and moving apart the 2 halves of our photodetector, leaving a gap in the middle, or equivalently just blocking out the light in the center. And then this bigger stair-step pattern over on the right actually approximates the correct weighting function even better. So this is to say, by effectively throwing away the center half of your laser, not detecting those photons, turns out you actually improve your signal noise of the quadrant photodetector. And so before we get to the experimental data, I like to read data sheets. This is a data sheet for a typical quadrant photodetector. They have a picture over here and they show the 4 quadrants. They show little gaps in between them. Prior to thinking about this carefully, I always cursed those little gaps and said, my photons are falling in the gap. That's where the largest intensity is. I must be losing signal noise. Turns out that's not true. We should actually ask our photodetector companies to make even sloppier photodetectors with bigger gaps in between them. Okay, so experimentally, how does this work? So we didn't saw a photodetector in half. What we did was take 2 half-circle mirrors, we call them D-shaped mirrors, and we put them right next to each other to make something that was almost a circle, but with a gap in between them. And we take all the photons that bounce off of one mirror and put them on one photodetector, all the photons that bounce off the other mirror, put them on the other photodetector, and we can move that gap apart. And we can go ahead and measure the signal. In this case, this would just be the thermal motion of a nanomechanical resonator that our light is bounced off of. We can measure the shot noise floor as a function of all the graphs at the bottom here. The function is the size of the gap compared to the beam waste, the optical Gaussian beam waste. And as you see, as we move our detector apart, the signal gets smaller. That's not surprising, fewer photons. The shot noise gets smaller, definitely not surprising. In absolute terms, there are fewer photons, so there's fewer the shot noise is smaller. If we take the signal to noise, it actually increases from 0 gap to removing about half of our light from by about a good fraction of a dB. So we go from this 64% to this 83% quantum efficiency just by blocking half of our light. So I think that's an experimentally useful technique to get us to something that's close to a quantum ideal measurement with a simple detector.
Is there something built into here that the detector noise floor is not your dominant?
Yes, yes. So yeah, that is an assumption here that the that what we're seeing, the noise floor of our measurement is optical shot noise. Indeed, yes. So that becomes less true as we have less total optical power hitting our photodetector. Indeed. Yeah, so in the limit where you have a fairly good detector electronics where your shot noise limited with your with your detection, this is what you expect to see, and this is what you do see. Question.
Tom?
Sorry, we have a question from the audience first, then we'll get to the Zoom. Question from the audience.
What are the red lines?
The red lines are a fit to just integrating out to your Gaussian with a gap in it, and so that's the theoretical prediction as to what you expect. Okay, and then Alan, you have a question on Zoom?
Yeah, it's Alan McDowell. You're sending the light and reflecting it off of one slope. I could imagine that if you had two beams and you reflected one off of one slope and one off of the other slope, you would get twice the deflection. Does that win you anything?
So this is the quantum efficiency of the measurement. It doesn't tell you about the measurement strength. So it turns out to get a better measurement strength, you actually want to make a, do I have a slide on this? I have a slide as much later. Let's talk about it now. We won't talk about it later. To get the best measurement, you need to shine light on the parts of your device that are moving the most, right? Now, that intuitively makes sense. And so to answer a simpler question, to get not just a better quantum efficiency, but to get overall better measurement strength, you want to make a Gaussian beam that's as big as possible, meaning that it encompasses almost an entire acoustic wavelength. And then you're actually getting light where your device is moving. The obvious way of saying that is that if your spot size on your device is bigger, the divergence angle of your beam is smaller. And what you're doing is trying to compare that divergence angle to the actual deflection angle. Well, then your signal noise goes up for a lower numerical aperture beam. There are plenty of other measurement techniques you could do, like concentrating light at two different antinodes and then interfering those in an interferometer is a fine way to go. And basically, these geometric factors, if you optimize different techniques, give you a slightly different signal to noise, but roughly at the factor of 2 level, if you get your beam geometry correct.
Okay, thanks.
Okay, so not to run out of time very quickly, we are running out of time very quickly. We haven't actually got to the, that's just about photodetectors. We haven't actually got to what actually happens to the device when we shine light on it. Well, what happens is that we make a measurement, we bounce photons off, there's some sort of back action. This is a general plot that is drawn to encompass this idea. On the horizontal axis, we have the optical power of light bouncing off of some object. And on the vertical axis, we have the noise of a measurement. And the noise comes from 2 sources. There's the shot noise floor, which if you have more and more photons per second, the random fluctuations in the number of photons average out. With more laser power, you get a better and better signal noise. That's the curve that goes down. There's the effects of what we call quantum back action. The fact that each photon that's bouncing off your device is giving it a recoil momentum kick. And that's that gets bigger and bigger with more power, more photons. The sum of those 2 things makes this black curve. The bottom here is called the standard quantum limit. It turns out that what this says is that for an ideal quantum measurement, the best you can do is add 1 0-point motion worth of extra noise on top of your measurement. And that's what we call the standard quantum limit, operating at that minimum of that black curve. So how does this play out in an optical lever? In an optical lever, what we have is some Gaussian beam bouncing off a lever and then going to some photodetector. It turns out that if that beam is exactly centered on the fulcrum of our lever on the node line of a mechanical mode, well, there's no average. The net force cancels out. What we need actually is a torque in order to spin a torsional resonator. We need some off-center beam. And how we get off-center beams here is actually we have a fundamentally occupied, we call it U00, that's the fundamental Hermite-Gauss polynomial mode, just the Gaussian mode. That's occupied with a coherent state. And that actually interferes with the vacuum fluctuations generated in the first order Hermite-Gauss polynomial mode. And that actually causes, that's what we say when we say quantum limited pointing fluctuations of a laser. The vacuum fluctuations of a 0-1 Hermite-Gauss mode are interfering with the coherently occupied fundamental Gaussian mode and effectively making our beam looks like it jiggles back and forth. And that puts a lever arm on our force, allows us to put a torque on our mechanical resonator, makes it jiggle about. That's the back action from our measurement. And of course, when it jiggles, the lever rotates, and that changes the angle of reflection, and that shows up as extra noise on our detector. So that's back action in the optical lever. Let's see. Just to say, no one's seen this yet. And that's because all the interesting optomechanics experiments to date really have been done in cavity optomechanics, meaning a high finesse cavity to have your light bounce off some mechanical object multiple times to enhance the interaction. Did all sorts of great stuff. Ground state cooling, squeeze light generation, quantum state transduction, back action evading measurements. Let's do that in a single pass without a high finesse optical interferometer. Takes some work. We need to build a high quality factor mechanical resonators to make up for effectively quality factor 1 optical resonator single pass. And here's some parameters over on the right. I don't know if they mean much to anybody, but we think we can get to an experimentally reasonable regime where, say, the random torque and random force on our nanomechanical resonator is larger than the thermal force noise in this optical lever setup. We haven't got there yet, but the data I'm going to show you is looking at a classical noise driving our mechanical resonator. So we built these, in order to do that, we need a high quality factor mechanical resonator. We built these strings. These strings have a few interesting properties. They can have very high quality factor for a lot of reasons. One, they're under high tension. The higher the tension, just like any guitar string, the higher the frequency. Turns out, as you tension a string with gigapascal tensile stress or more, the resonance frequency goes way up. It depends on its aspect ratio. These are very high aspect ratio, millimeters long, 100 nanometers thick, and it's very floppy without any tension. And we up the tension, we up the frequency by orders of magnitude. Turns out we don't change the intrinsic dissipation very much. So the quality factor goes way up. Because frequency goes up, dissipation stays the same. That's called dissipation dilution. At the same time, maybe it's better shown on this diagram, we also periodically modulate the string. That's another example of a phononic crystal. That is, when we periodically modulate the width, we're changing the speed of sound in different sections of our string. Every time we have an interface with differing speed of sounds, we get a little reflection. And if everything is geometry set up right, all those reflections add up coherently. We've made a couple of acoustic mirrors that trap a mechanical mode at the center of the string and don't allow it to get to the ends. Right at the clamping points of the string is where a lot of dissipation tends to happen. So we can trap a mode in the center of a string under high tension and get a pretty high quality factor. And this is ideas we've stolen from some other groups. It goes under the idea again of phononic band structure, phononic crystal engineering. Don't have time to talk about that. Here's our devices. Our best effort to date. We can make a Q of 10 to the 8 megahertz mechanical resonator at 4 Kelvin. And is that good? That turns out that that string will oscillate for about 1,000 times before one thermal phonon hops on or off our mechanical resonator. So it's quantum coherent for about 1,000 oscillations. That's pretty good as a general figure of merit. Let's see. Let's skip all this since we talked about this. So how do we evade back action in an optical lever? We talked about what the back action is. There's actually a really easy way to get around measurement back action. So this is a very simple diagram. Some light bounces off of our moving object or tilting object, and it gets deflected. So if this object is just driven by an external force, all of our rays will just get deflected more than we go to one side of the photodetector than the other. But let's ask ourselves what happens if that motion is driven by optical back action. So the idea here is this red ray, if it hits the fulcrum, it doesn't put put a torque on our torsional resonator, and it just goes straight to the center of the photodetector. This off-axis ray in green on the left, what it's going to do, it's off-axis, it's going to push on the optical lever, change the angle, and that's going to create an angular deviation, which changes the location on our photodetector. The thing to remember is that the torque is R cross F. So as we increase our lever arm, as our ray gets further away, the angular deviation is larger. And the way I think about this then is, what other optical element does that? Well, either a convex mirror or a diverging lens. So effectively what we've got here is a dynamical lens. That's one way to characterize the back action in an optical lever. It's effectively diverging the rays. Because as you push on the lever, the further out you push, the bigger the tilt, the larger the angle of deflection. Well, there's a very simple prescription to undo the effect of a diverging lens, and that's to put in another lens to counteract that. So it turns out that in order to defeat the back action in an optical lever, all you got to do is add a lens after you detect after you notch the light.
5 minutes, I'll be done. There's a talk. I'll be done in 5 minutes.
Okay, well, anyway. We'll be done in 5 minutes. That's a good point. Just to get to the data very quickly, so I've gone through all this description of how an optical lever should look like. It turns out that we have this lens, and now we can undo the effects of our dynamical lens just by adding that lens and then moving our detector on the left here down to where those effects are undone. And it's just that simple. So how does it work in practice? We have some setup that does that. We want to put our detector with what's called the Fourier planar lens in order to get rid of the effects of noise. To actually do this, we do an experiment with classical pointing noise. That is, we take an acousto-optic modulator, which changes the location, the angular deflection of some laser beam that goes through it. We FM modulate that to create a classical pointing fluctuation in our beam, and we measure the output with our quadrant photodetector. And it's a very simple optical setup. This is what happens if we put our detector right at the Fourier plane, where the optical system has the AOM has changed the location of the beam, and then all the optics undo that at a certain location along the beam path. If we move our detector just a tiny bit along the beam path, we actually end up with curves like this. So this is the driven response. So what we're doing is sweeping the frequency of our modulation over mechanical resonance and looking at the response on our photodetector. So anywhere where these yellow or blue curves, one is moving it forward along the beam path, one is moving it backwards along the beam path, orange and blue. Anywhere where they're below the black, that means we've actually reduced our sensitivity to pointing fluctuations causing back action on our system. So this is classical noise reduction. If it were quantum noise, this would actually correspond to squeeze light coming out of our system, and our signal noise would go up. So we're almost out of time here, but you can move your detector further along and come out with some nice, interesting beam shapes. And you can actually go ahead and take all those spectra and plot them in a nice color picture, frequency on the horizontal axis, and actually detector location on the vertical axis. And we have some theory which says how big the response is supposed to be in this density plot. And our experiment's not too far off. So everywhere where you see in blue, that means you're suppressing the response below what you would naively expect if you weren't canceling out these fluctuations with your extra lens. Okay, so I think I'm running out of time here. So eventually we want to do this in a quantum regime, see squeeze light, make measurements that actually beat the standard quantum limit. And this part 3, as I expected, I don't have any time to talk about. We're also building quantum transducers that couple optical and microwave signals. We've got a couple different endeavors. One that goes through a piezoelectric element, one that goes through an electro-optic transducer. And I'm happy to talk to you about that later at lunch or whoever meetings, or you can email me if you want to talk about all of our electro-optic transducers. So I'll skip through all this. We're building very large microwave photonic crystals to make an electro-optic transducer. For those of you who are used to seeing optical photonic crystals, these are the same, but microwave wavelengths are very large. You can make more complicated structures in the microwave domain than you can in the optical domain, because you can conventionally machine things with pretty tight tolerances. With that, let me just again acknowledge all my group members. They're doing great hard work. We got a lot of collaborators here, and let me just say that we're interested in eventually putting all this fun high precision measurement technology to work to measure some small things. With that, I think I'll conclude. Thanks. What questions? Yeah.
Yeah, so I have two questions.
Sure.
The first one is regarding the mechanical detector. The actual measurement is through the direct imaging of the oscillations of the resonator, or it emits photons after it absorbs the photon.
Say that one more time.
Yeah, for the first
for the
mechanical oscillator. So how do you actually detect the absorption of a photon?
We measure the amplitude of motion of the silicon nitride surface with an optical lever detector.
Okay.
So
is that direct imaging of the oscillation?
yeah, we're just measuring the amplitude of oscillation at a single location, but we assume that the mechanical modes are still high enough Q that all of the signal at that frequency is in the particular spatial mechanical mode that I showed.
Okay. And the second question was actually related with the Q factor, because you have a very high Q factor as you showed, but you're measuring something very broad because your body is very broadly has many frequencies, I guess. So how is the relation? How strong should the oscillation be? So how should the amplitude of the oscillation be to be able to be detected? Because you have only a narrow, you can only detect a narrow portion of it.
Yeah, so we are detecting. So the assumption is that the acoustic blackbody radiation in the substrate is very broadband, and effectively it's white noise over a very wide range of frequencies. So it's just like it's not exactly like electromagnetic blackbody radiation, but it's peaked broadly in the near infrared. In the tens of terahertz frequencies, probably in the acoustic domain, the same as in the optical domain. So in the frequencies we care about, it's basically just white flat noise. And we did some experiments that say we can detect 10 atometers per root hertz motion in the substrate with our optical optomechanical readout. So it's actually a pretty sensitive detector of motion of the substrate. If that motion is in the particular mechanical shape that couples correctly to a particular mechanical mode. So there's a particular radiation pattern in the substrate with roughly 10 atometers of motion, and we can detect that. Question?
Could you elaborate a little more about the tabletop of gravitational wave detection?
Yeah, you saw that on there. I got all sorts of aspirations. One thing I like is that these silicon nitride strings can have very high quality factor, which means their resonance frequency is very well defined, right? And turns out that if you stretch them a little bit, they're actually a very good sensor of length differences. And I don't know if it'll ever work out, but I have aspirations as to make that, so to use an acoustic wave interferometer as opposed to an optical wave interferometer to measure the distances between test masses. It's hard. If you go to the very highest Q we could get to, the very lowest possible temperatures you could possibly get to in a dilution refrigerator, the biggest masses you think you could fit on a tabletop, the numbers are not physically impossible. Is what I'm going to say about that. But I think we are interested in exploring strain sensing with these silicon nitride strings. We actually have an experiment where we built silicon nitride strings on a stretchable frame, so we can actually physically change the end lengths and watch the resonance frequency change. And we want to understand a lot of stuff about that, how good of a strain sensor it is, what sort of mechanical parametric resonators and mechanical parametric amplifiers and converters we can make in a system like that. And we're just getting that set up, so I don't have any experimental data, but we have our first sets of stretchable strings fabricating. We're working on getting them in a test setup at the moment. So it's very, very far down the road.
How often do these strings just tear. I remember hearing horror stories about the Kimball Lab, like alligator cavities under gigapascal strain, and they would just like give way after a month of a bit of steam or something.
Well, yeah, so we just have in a vacuum chamber. We don't have any corrosive gases in there. And you can see that my students are actually able to make fairly high yield string. So this is an array of like 10 strings. They're equally spaced, meaning that they aren't all broken. I think, so it is possible. The silicon nitride is a pretty tough material. It can survive going into liquid. It can survive cooling down to cryogenic temperatures. Yeah, we haven't tried it in any gas that's not just, air or nitrogen or regular atmospheric gases.
Sounds like you don't have that problem.
Well, as soon as we start stretching these things, I'm sure we're going to break them. So the
So like, is it due to kind of like the necking, like you kind of go past the elastic, stretch it past the elastic regime, and then it kind of does this thing? Is this
I
what
don't
you're
know.
referring to?
I know that they were, silicon nitride, optical photonic crystals, and some long combination of the cavity and then some shield or whatever, and that they would just sort of break constantly, and so they had to open the vacuum chamber, replace it. Maybe Bill knows more about this story. I've heard some noise. Bill?
he's got his hand up.
Well, yeah. Actually, I had a different question. I'm not sure I really have any of the knowledge that that's being asked for here. But my question is this, if I may.
Sure.
One of the things we always think about when we think about radiative blackbody is the Planck radiation formula, the fact that I can't get it classically, that I have to introduce some kind of a quantum understanding of the way in which energy is exchanged. Now, you've emphasized a number of times that you are generally thinking of this thermal blackbody radiation as being white, but of course it's not. And what I'm wondering is there in fact that same situation for acoustic blackbody radiation? Does it have a Planck-like law? That is, does it show that that there's a quantum exchange of energy? And what would it take to see that, if it is that?
So yeah, that's an interesting question that I would have liked to have thought about, and I've done very little thought on that. I think one difference is that these acoustic waves have to exist in some medium. So you intrinsically have to understand the properties of the medium, be it solid, liquid, or gas. And so it somehow feels to me less fundamental because, say, the dispersion of the medium is going to be a function of wavelength. So you're not going to get a simple radiation law that can be tested independent of the fine details of your material properties. But I would imagine if you make some assumptions about a truly isotropic, infinitesimal, a truly smooth medium, there probably are some laws you can derive. But don't take my word for that. Jay, you have a question or comment telling me I'm right or wrong? Okay.
This discussion. I mean, if your temperature, ultimately the phonons also obey a full Bose distribution.
Yeah.
And so there will be the boundary for like whatever temperature, if you get a cutoff, and if you lower the temperature,
it's the exact same derivation,
Yeah.
especially if you get the temperature low enough so that you're in the linear portion
Yeah.
of the acoustic phonon.
that's all.
If you're too high for that, then things change. But the phonon gas and the photon gas at low temperatures, they have to be in that interval.
Yeah, that's what I would have guessed. Yeah, I don't know if people heard on the internet, but it said that, the people who know about these kind of derivations would believe that photon and phonon gases behave similar in the limit where you're, say, cold enough that your phonon gas is in the linear regime of the medium. So you can just call it an isotropic medium.
Yeah, not that cold necessarily.
Oh. Okay.